All right, so drawing this 5-membered ring from our clicker question, the question is, why is this actually acidic? Why is that going to be acidic? So we're going to have to react it with a base, so just OH minus. So it's going to deprotonate. This is going to be our acid. So break the carbon hydrogen bond. There go the electrons. And what we form is a carbanion. But for some reason, this carbanion is especially stable, right? And it's telling us why this is really reactive. Because it doesn't look like a regular very reactive bond. It's just a CH bond. But when we form this product, if you look at this product, it has a p orbital system. It's uninterrupted. Right? It's in a ring. It's all conjugated or delocalized. Right? And what that means then, it could be aromatic. And then we got to look at how many pairs of electrons are actually in that ring. So if you look here, you could say 1, 2, 3. 3 is an odd number. So that would indicate to me that this is aromatic, right? And of course, that carbon there that I'm highlighting there is choosing to be sp2 hybridized, so it has a p orbital. It can put that lone pair and delocalize it into the p orbital system. So this is an aromatic compound. So that tells us something about this. So anytime a reaction takes place, you could either have or have both really fast or really stable starting materials, or really reactive starting materials, and or stable products. And what are the three things that dictate aromaticity? It has to be planar, it has to be uninterrupted in a ring, it has to have an odd number of pairs of electrons. I would add, it also has to be into a ring, of course. Odd pair of electrons, but also in a ring. All right, so this are the 4 questions we have before. So these are all 4 compounds. If they lost a Br minus, they'd be a carbocation. What would they be? Would they be aromatic? And that's kind of the question we're looking at here. So let's break down each one of these to see if that's possible. So to show this, the first thing, you have a leaving group. So the bromine for each of these is going to have to leave. So to show electrons that are flowing, breaking that carbon-bromine bond, that's what's going to happen in every single one of these. So we're going to create a carbocation for each of these, and one of these carbocations is going to be an aromatic species, and that's what we're going to examine next. But we got to be careful about which ones are which. So if you look at these, a lot of it's the same thing kind of happening here, but very specific. We remember about aromaticity is planarity, uninterrupted pi systems. All right, so there's A, B, C, and D, and an odd number of pairs of electrons. So let's break this down. All right, so very good. Breaking the carbon-bromine bonds, A, B, C, D. And a majority of us actually answered the wrong ones here, so we got to break this down and really think about it differently. All right, so let's examine A here. So what's going on here with A? So the carbon-bromine bond breaks, and we form a new carbocation, but we got to be careful with this. So it's uninterrupted, it's a ring, has a uninterrupted sp2 carbocation in there, but we got to be a little cautious because this actually makes something that's anti-aromatic. It's in a ring, but it has an even number of pairs of electrons. Uninterrupted in a ring, it actually makes something that's anti-aromatic, which is, of course, is be much less stable and not what we're looking for. Be careful here. Of course, we have a Br minus as well. But yes, again, anti-aromaticity. So that's really, really unstable. All right, let's break down B. So what happens with B? So B has an aromatic ring, of course, but when that carbon-bromine bond breaks, the empty orbital is actually an sp2 hybridized orbital. Right, that's an sp2 hybridized carbon. And when that carbon-bromine sigma bond breaks, that was an sp2 hybrid orbital there, forming that bond. So when we have a carbocation when it's empty, it's not part of the p orbital system. It can't do resonance. So this is actually really unstable and very unlikely to be formed. Like I said, I would call it non-aromatic. It's really kind of aromatic. I wouldn't really put a question like this on there. It'd be kind of tough to do, but we could recognize that can't do resonance. So that's really, really unstable for this case. Right, D. What if we have that carbon-bromine bond break? What are we going to make in that case? A large ring, of course, and a carbocation. It's going to be able to do resonance, but it's not going to be aromatic, right? So there's our carbocation. It can do resonance, and of course our Br minus. But we're not going to be able to do resonance. We're going to be able to do resonance, but it's not going to be aromatic because of this.
And what's wrong with this one?
It's not an uninterrupted p orbital system, right? There's an sp3 hybridized carbon there, so it can't be aromatic, right? So this is definitely non-aromatic. Right? And then the other one, this one would be aromatic because, right, what happened? Uninterrupted p orbital system. It's all in a ring, and there's 1, 2, 3 pairs of electrons in the system. Aromatic.